Hello 108 students, Mr. McHugh here with you. Welcome to section 4.1 where we are going to tackle systems of linear equations, which basically where do two lines intersect, and we want to find that solution of the common x comma y ordered pair that will make both equations true. Okay, so it's kind of a fancy name, but if you are given two lines and you have your equations, can you find the solution or the intersecting point that value of the ordered pair x comma y that will make both of them true? Okay, now there's a lot of real life practical applications of this usage. It's one of the first places I saw in business situations where you could use this, and what I want to draw here is, if you look on page 210 of your notes, you'll have, they have the sale of digital cameras, and they do the sale of digital camcorders, but I want to change that around a little bit, and I just want you to think about this just to understand if you have the ability with math tools to help you out. So here's a graph of x comma y, and let's let x be years, and starting from the year 2000, this is 2001, 2002, 3, 4, 5. So not too far back, around 10 years ago, we had an increase in the sale of digital cameras. Now it's funny how common they are now, but there was a time where the old 35mm cameras existed. So on the y-axis, what if we put sales of money? Okay, how much money would you get from the sale of digital cameras as compared to the 35mm? Now I just want to show and illustrate something here. This is not accurate real data, but back in 2000, I'm going to draw a line. It's going to go up. It's an increasing, and I'm going to let that be digital cameras. Okay, I'm just going to let that represent that, and maybe in the year 2000 there was 100 million. Again, I'm just making numbers up. It doesn't really matter, but the concept is, as the sale of digital cameras were going up, but what was a couple factors for that? Well, the price kept going down, right? If you remember all this, and people were more open to it. Now, you go back far enough, you remember 35mm cameras, you needed film. Film kept getting more and more expensive, so a lot of factors were going in place. And what happens if you saw something like this? This is the sale of your 35mm cameras. Every year, you see the price of it going down. And imagine if you had the linear equations for these two graphs, and you were an analyst for Kodak, and this has kind of got a real life connotation to it. Here's Kodak. They made 35mm cameras. They were the king of making them. Okay, you're walking around, you're seeing your sales drop of 35mm, and they keep dropping, and you hear about these digital cameras. You think, oh, they're never going to take off. Who would ever buy those things? You get no film. Look what happens if you could go to your if Kodak the company would have realized these trends and plotted out these simple linear equations and realized that somewhere around the year 2002, according to my rough unofficial estimates, that was the turning point of where the sales of digital cameras and analog cameras were the same. What happened as you went every year after that? The sale of, let's go just 2 years later, look at the difference here. The sale of 35mm is dropping dramatically. The sale of digital cameras is going up increasingly fast every year. Now, if you're in the business of making cameras, what kind of cameras do you think you should make? Yeah, eventually digital took over. And unfortunately, Kodak maybe did not recognize that situation quick enough, and now they no longer are going out of business. It's kind of a sad story. But I hate to illustrate bad news with that, but the idea that you can analyze, use algebra and linear equations to help you predict has very practical applications. Okay, we'll do another case down the road where you do break even. Okay, now let's get back to the algebra part of it. This example one here I have is, how can you figure out whether an ordered pair is a solution to both equations? You simply take the values of the x comma y, substitute them into the two different equations, take the y value and substitute it into both equations, and see if they happen to be true for both of them. So I do that real quick here. You put 4 in for x, 2 in for y, 4 plus 2 is 6, and yes, that's a true statement. Come over here, you put 4 in for x, 2 in for y, 4 times 4 is 16, minus 2 is 14, and yes, that is true. Now, this is a very awkward way. This is not a way to figure out the solution of where two lines intersect, but it is a way to verify, and I want to keep that concept in mind. When you find a solution doing these other techniques, you can always take that ordered pair that you find as a solution, substitute them back into both equations. If both equations are true with those values of x comma y, the ordered pair, then you know you have the right intersection. Okay, so with that said, objective 2 here on this page, we are going to go ahead and solve by graphing. This I kind of like doing this. If you have a fairly easy equations, you have graph paper, and you're accurate with your graphing onto the grid, you could take an equation like x plus y equals 5 and 2x minus y equals 4 and go back and graph them. Okay, now you could turn around. There goes the ice cream van going by. You could turn around and look at this. How would I do this? Isolate the y equals mx plus b. Slope is -1. Y-intercept is 5. Can I graph that? I come up here to 5. The y-intercept, slope is -1. That's equivalent to what? -1 divided by a +1. Down 1 over 1. Down 1 over 1. Okay, so we're graphing this guy right here. That's where he's there. And now we come over here to 2x minus y equals 4. Isolate for y. Now watch your algebra a little bit. Minus 2x on both sides. Now you need to have a minus. You always solve for a positive, so you need to multiply everything by a -1. Now you do this enough times, the shortcut is to tell yourself to flip the sign of every term in the equation. Now here's a positive, a negative turns into a positive, and a positive turns into a negative. Okay, but you multiply the equation by -1. Now can you find the y-intercept? There's -4 and the slope is 2, which could be written as 2 over 1. So we come down to -4 and we do slope of up 2 over 1, up 2 over 1, and boom, we hit it right there. Okay, now the question is, what is that ordered pair? From the graph, starting from the origin, I go over 1, 2, 3, I come up, I come back over to the y-axis, and I'm hit at 2. So the OR solution is 3, 2. Now does that make sense? Use this technique up here. X is 3, y is 2, come up to the equation. Right here, 3 plus 2 equals 5. Is that a true statement? That one's extremely easy, so it looks encouraging. Let's take this guy. Let's see if I can squeeze it in here. 2x minus y equals 4. Okay, x has got a value of 3. Y has a value of 2. Does that equal 4? So you've got 6 minus 2. Does it equal 4? And good news is 4 does equal 4, and boom, you verified it. Okay, so that's the idea. I'm hoping you guys, this is a new material again from section 2.5. I'm sorry, from 025. I apologize. From 025, just like functions were. So what you're quickly finding out here is that 108 has got a fast review of 025. The first half of the course, we will go through chapters 1 through 7. Fairly quick, but more in depth. And then once we hit chapter 8 with radicals, we will be basically covering new material from there on in. Okay, Ms. McHugh here for now. I'm going to sign out, and I will see you on page 2. Okay, bye.